Good morning. Thank you for your kind invitation to Bionetics 2010. My name is Massimiliano Versace. I work at the Department of Cognitive and Neurosystem at Boston University. And the title of today's talk is Brain-Inspired Computing. So one of the fundamental themes of Bionetics is how do you take inspiration from biological computation and use this fundamental intuition to build, for instance, better technology. So my talk today is focusing on a subset of this general problem, which is how do you use intuition from the way that the brain computes information in order to build better machines. And if you look at the panorama of various attempts to build intelligent machines, you find that there's been tremendous advances in fields such as robotics, neuroscience, computational neuroscience, computer science, and engineering to try to get us closer to the target. But I think that most of you also would agree that the promise of a truly intelligent and autonomous intelligence still has to be fulfilled. And I would argue that there are two main set of challenges that are interlinked between us and this main goal. The first pertain modeling. So it is a challenge to build a small-scale network, for instance, that simulates aspects of intelligence, ranging, for instance, from visual perception, auditory perception, planning, spatial navigation, emotion, etc. It is another source of a challenge to integrate all these different models, which might be expressed at different granularity, for instance, into a whole brain system that can then be integrated in a mobile robotic platform. A parallel set of challenges is the hardware. So what kind of hardware can you use in order to implement these large-scale whole brain systems? And how do you then take this hardware and scale it down by reducing mostly its two most challenging dimensions, which are size and power consumption, in order to create a smaller hardware device that can be then embedded in mobile robotic applications. So the first set of challenges is the hardware, and if you look at the way people in my field, for instance, simulate large-scale whole brain system is by using traditional von Neumann machines. And yes, it is true that advances in miniaturization of transistor had led us to pack more and more computing power in smaller and smaller devices, but it is also true that we are approaching a limit for this exponential increase in computing power, which is due to the fact that as you scale transistor down to the nano size, there are issues related to extreme miniaturization, power dissipation, etc., that basically will stop this progress one day pretty soon. And this can be also seen, for instance, by the bending curve of the clock of each individual, for instance, processor. You can find commercially available multi-core processors getting more and more traction, but you will find that the clock of each individual processors has kind of plateaued. Another source of problems with conventional von Neumann architecture is the physical separation between, on the one hand, the processing of information, and on the other hand, where this information is stored in memory. And whenever you introduce such a bottleneck, you introduce issues such as power consumption, power dissipation, or communication bottleneck. So it is no mystery that many players in the computer industry and also in the governmental agency are looking at alternative ways in which you can compute information, which is, for instance, overcoming some of these main bottlenecks. And the question is, what kind of computing device out there, for instance, in biology, merges computation and memory in order to overcome this communication bottleneck? And the answer is, not surprisingly, the brain. One of these agencies, DARPA, is known for futuristic and kind of extreme projects in general, and one of these such a project is called Synapse, which stands for a System of Neuromorphic Adaptive Plastical Scalable Electronics. It is a program that I'm going to illustrate briefly today, and this is where most of the work that I'm presenting in this talk is actually focused. The program seeks to find a solution for the imminent failure of Moore's law for conventional chip. The goal of Synapse is to enable electronic neuromorphic machine technology that is scalable to biological levels. And the program rests on two basic assumptions. The first is that traditional algorithms tend to perform poorly in situations where biological computation instead thrives, and traditional microprocessors, on the other hand, are just the wrong hardware to implement data-intensive and data-distributed algorithms that are typical of biological intelligence. The following two slides are actually courtesy of the DARPA program manager, the Synapse program manager Todd Hilton. So DARPA is a very complex problem that is tackling many different issues almost simultaneously. The first is to create synapses. Synapses are uh, the dominant component in the communication between neurons. Each neuron has between 1,000 and 10,000 synapses. So the main question is, how do you realize this plastic element, a communication element between neurons, by while at the same time maintaining a low power and a low physical size for these components. Once you come up with these synapses, how do you embed them and make them talk to a neuron, so you can create a standard, for instance, a standard neuron for an electronic circuit. Once you have that, how do you assemble many neurons and synapses in order to create structures? For instance, how do you create a mini column, a cortical mini column, which is regarded by many as the main computing element of the cerebral cortex. So once you have that, how do you embed many of these mini columns in a larger chip so that you can progressively bridge the gap in terms of size and power consumption between a biological brain and and um, and the silicon one? Synapse is a fairly complex project which has several phases. We are currently at the end of phase one. It has, of course, a very heavy component in terms of hardware, so the idea is to come up with basic hardware characterization of devices such as synapses, assemble these synapses in larger components which include neurons, create mini columns, create larger structures, and then finally put together a system which has multiple chips that are able then to be transferred in mobile robotic application, if we of course maintain the right balance between size and power. Architecture and simulations are two of the main components here, and the idea is to create a large-scale brain simulation that can exploit and comply with the architecture of the hardware that is created. And environment is actually one of the key aspects of what we are doing. So we are testing these large-scale brain models, implementing this newly developed hardware architecture in a virtual environment at the beginning, in which we test basically the ability of our whole brain system to produce intelligent behavior, and progressively test more and more of this brain architecture in mobile robotic platforms. So Synapse is funding currently three companies. One is Hewlett-Packard, the other one is Hughes Research Lab, or HRL, and both of these companies are actually working with Boston University, and the third one is IBM. The talk that I'm giving today pertains the work between Hewlett-Packard and Boston University. So the goal of the project, again, is very ambitious, is to come up with a hardware implementation that roughly has the same number of neurons and synapses as at the end of the project as the human brain, with a slightly higher power consumption. The goal is to create a multi-chip architecture that we like to call a shoebox, which will have at the end of the project roughly 10,000 chips for a power consumption of around 1,000 watts. And if you wonder what is exactly 1,000 watts in common language, if you go in a common house, you can find that the microwave oven has around 800 watts, and the dishwasher around 1,500 watts. And it's no surprise that the espresso machine, which is the most perfect machine ever created by humankind, has around 1,000 watts. In case you ask what will take us to implement such a system in conventional hardware, the answer is a lot of real estate, roughly a couple of rooms of the size in the one we are presently in, and the reason is that it's just the wrong hardware, the wrong metaphor in order to implement biologically scaled circuits, which are often characterized as a stiff nonlinear differential equation, and digital hardware tends to be not the best solution for this problem. The project would have not been possible without the introduction of a memristor, which is a novel electrical component which flanks a resistor, capacitor, and inductor. Memristor was initially theorized by Leon Chua in the 70s and was then discovered experimentally by our collaborators at Hewlett-Packard, in particular a team led by Stan Williams and Greg Snyder. A memristor is basically a resistor with memory, so it's a resistor that remembers its past history of stimulation, and it is an electrical component that has evaded characterization in the past decades because of the fact that it starts to emerge at the nanoscale level. What we're going to do with Hewlett Packard is basically co-develop, on the one hand, a hardware architecture that takes maximal advantage of the merging between computation and memory, and on the other hand, large-scale brain structure that implement complex adaptive functions. In phase one, we are primarily focusing on virtual environment. So the idea here is to test the aspect of the whole brain system in a virtual environment, which in this case replicates some key rodent experimental results. But what we are doing already in phase one, and what we plan to do more heavily in phase two and three and 4, if it exists, is to move more and more towards mobile robotic applications. I will illustrate three main projects that we are working on currently at Boston University in collaboration with Hewlett Packard. The first is learning, and the goal here is to analyze a large set of learning rules that will inform chip design. The second is the animate, which is our main project, and the idea here is to create an intelligent agent that is able to intelligently, we hope, navigate a virtual environment and replicate some key rodent behavior. The third project is infrastructure, so we need a software framework that will allow us to rapidly prototype and iteratively select the best whole brain system model in order to power our virtual and real robotic animate. So I will briefly touch on what is the status at the end of phase 1 and some of the things that we would like to do in the upcoming phase 2. So the first project is learning. Synapse as the word learning or synaptic plasticity in it. So it's one of the key aspects of both the hardware and the modeling that we are doing. The first task that we are trying to accomplish is to find a general form equation that will allow us to include as many learning laws as possible in the hardware design. And the second one is an example of an implementation of one of these particular or a set of these particular learning laws in order to learn something meaningful. And what we did is to focus on visual learning, in particular learning of unsupervised learning of visual features. So if you scan the learning literature and try to figure out what kind of learning laws you will need to create an agent that has a large set of brain areas, and what you will need to give this agent the ability to learn in a supervised or unsupervised way in an unconstrained environment, you find that there is a huge variety of different learning laws. And with each learning law is usually associated a model which has oftentimes a different granularity from one to the other. So when you have different granularities, chances are that the learning laws are also different. And what is the choice? The choice that we decided to pursue is flexibility. So until we are pretty sure of what kind of learning laws we will need in the anima we want to build, we want to keep our option as open as possible, and that's basically our strategy. The flexibility that is actually needed for the choice of a particular learning law is given by the software architecture that we're using. Cog Ex Machina, that's the name of the framework, has been designed by the HP primary investigator Greg Snyder, and it is basically a software layer that we like to call the glue between, on the one hand, virtual environment or robotic interface and the whole brain system models, and on the other hand, a computational engine. So until the until the memory stiff engine, which are these large-scale distributed processor with integrated memory stiff based memory, is actually